Today we're going to go over definitive integrals, which is just a way to integrate a function within a bounded area. And before we look at these principles, I should elaborate on what a bounded integral is. And it's simply just the integral of f of x from b to a. And let me give you an example. Let's say you have the function x squared. This is its graph. And this is second one and this is second two. You want to find the area covered by f of x from second one to second two. So you're going to set up the integral from 1 to 2 of f of x squared. And it's simply just the area underneath the graph from 1 to 2. That is visually what bounded integration looks like. And let's say that there was a runner, for example, traveling at a speed of x squared, and you wanted to find the distance covered from second one to second two. Well, this is the integral you'd use. But let's get into the fundamentals. So if you have a function, or if you have an integral from b to a of n f of x dx, where n is a constant, it could be 2 or e, it doesn't matter as long as it's a constant. You can take out that constant and it will remain the same. Now, the second principle states that the integral from b to a of f of x plus or minus g of x dx is equal to the integral from b to a f of x dx plus or minus the integral from b to a of g of x dx. And this is just essentially stating that you can turn one integral, you can split it into two if you have two functions that are being added together or subtracted from one another. This one over here, the third one, states that the integral from b to a of f of x dx is equal to the negative version, the negative of the integral from a to b f of x dx. And you may think at first that there's no difference between these two. We're just flipping the parameters. So instead of going, for example, from 1 to 2, we're going from 2 to 1. And that's essentially just going to be the negative of the function of this integral. The final principle states that the integral from a to a f of x dx is equal to 0. And this one really, it's pretty intuitive. There can be no distance traveled if the time is equal to 0. Okay, let's get into the formula for finding the answer to a bounded integral. Essentially, you're just going to integrate the function normally. So if you have the function a to b of f prime of x, or just f of x, any function, dx, what you're going to do first is you're going to find the integral of f prime of x, or f of x. The integral of f prime of x is f of x, so we're going to start with that. Now, you do not need to put plus c. If the area is bounded, you do not need that extra variable that represents a constant. But now that you've found f of x, you're going to want to find f of a minus f of b. And it's really quite simple. You just substitute a or b in for x. And I stated earlier that the distance traveled, the integral from b to a of f prime of x dx is equal to the total distance traveled. And this is known as the net change theorem. It's pretty useful. All right, let's get into the examples. We're going to try to find the integral from 0 to 3 of x squared dx. And like I said earlier, you're going to start off by integrating the function. Now, what's the integral of x squared? It's 1/3 x cubed. Like I said, we don't need to put plus c, but we do need to specify that it's from 3 to 0. And now we're going to incorporate those constants, not constants, just integers. So we're going to substitute 3 in for x, and we're going to subtract 1/3 0 cubed because we substitute 0 in for x. Now this is equal to 0. This is equal to 9. So this entire integral is equal to 9. Okay, this is example problem 2. The first thing you may notice about this integral is that it has a constant, and that is 2. And you may recall that one of the earlier principles we learned was that you can factor out the constant of a function and it will remain the same. So this function, this integral over here is equal to 2 times the integral from 1 to 2, 1 over x dx. And you may recall that the integral of 1 over x is equal to natural log x. And so this integral is equal to 2 times natural log x from 1 to 2. Now let's substitute into an 2 and 1. So this integral is equal to 2 times natural log 2 minus 2 times natural log 1. And natural log 1 is equal to 0. So this entire integral is equal to 2 times natural log 2.